Hello! In this video, we are going to prove the following theorem. Suppose R and S are relations. R is a relation from A to B, and S is a relation from B to C. Then, the inverse of S compose R is equal to R inverse compose S inverse. Now, first, I would like to mention that both of these sets are relations from C to A. And to see why this is true, first of all, we're given that R is a relation from A to B. We're also given that S is a relation from B to C. Now notice, R goes from A to B and S goes from B to C. So really, R and S form a composition that goes from A to C. But which relation do we write first? Do we write R or S first? Well, if you recall, the first relation is the one that contains the second set, and the second relation is the one that contains the first set. So really, the first relation is the one that contains C, which we see is S. And the second relation is the one that contains A, which is R. So really, we have that S compose R is a relation from A to C. Now, if we take the inverse of S compose R, if you recall, that's just going to swap A and C around. So we get that the inverse of S compose R is a relation from C to A. So as we can see, yeah, the inverse of S compose R is in fact a relation from C to A. Okay, so then what about R inverse compose S inverse? Well, if we take the inverse of R, then that's just going to swap A and B around. We have that R inverse is a relation from B to A. Similarly, if we take the inverse of S, that'll just swap B and C around, right? S inverse is a relation from C to B. Now notice, S inverse goes from C to B, and R inverse goes from B to A. So, R inverse and S inverse form a composition that goes from C to A. But again, which relation comes first? Again, if you recall, the first relation is the one that contains the second set, and the second relation is the one that contains the first set. So really, the first relation is the one that contains A, which in this case is R inverse. The second relation is the one that will contain C, which is S inverse. So we have R inverse compose S inverse is a relation from C to A. Exactly what we wrote right here. So that verifies that this is true. But why did I even mention it? Well, notice what we're trying to prove. We're trying to prove that two sets are equal. What does it mean to prove that these two sets are equal? Well, this is equivalent to saying that for all objects Q, Q is an element of this set if and only if Q is an element of this set. So really, this is what we're trying to prove. But wait a minute, where do our objects Q come from? Well, because both of these sets are subsets of C times A, we could think of our objects Q as though we're pulling them from the larger set, C times A. So really, this is the statement we're going to prove. Now really, we're trying to prove a statement about all elements in C times A, so give me an arbitrary element in C times A. Now, we know that all elements of C times A are ordered pairs, so we'll say that our arbitrary element is the ordered pair C comma A. And now, we want to show that C comma A is an element of S compose R inverse if and only if C comma A is an element of R inverse compose S inverse. And we're going to do so by establishing a chain of if and only ifs. Now, let's start by writing that C comma A is an element of S compose R inverse if and only if what? Right? We need to find a statement that is equivalent to this one. Now, if you recall from the inverse of a relation, we know that this is equivalent to if we just swap the order of C and A and write that A comma C is an element of S compose R without the inverse. Okay, so then what statement is equivalent to this one? Well, notice our composition contains R and S, right? R goes from A to B, and S goes from B to C. So B is our intermediate set. What does it mean to be an element of this composition? Well, it means that there exists an element in our intermediate set B, say B, such that A comma B is an element of R, and B comma C is an element of S. Right, so this is what it means by definition to be an element of this composition. So that's why they're equivalent. Now notice, inside of the statement, we have A comma B is an element of R, and again, by inverses of relations, we know that this is equivalent to if we just swap the order of A and B and write that B comma A is an element of R inverse. And similarly, to say that B comma C is an element of S is equivalent to if we swap the order of B and C and write that C comma B is an element of S inverse. Okay, so next I'm just going to swap these two statements around. Right, conjunctions don't care about the order of their statements. Okay, so this is where we're at. But it turns out this is what it means by definition for C comma A to be an element of R inverse compose S inverse. The reason why is because it's exactly analogous to why these two statements are equivalent. Right? Notice in the second statement, we can conclude that A comma C is an element of S compose R, right? A comma C is an element of S compose R. Same thing right here. We can conclude that C comma A is an element of R inverse compose S inverse. Right? That just comes from the definition of compositions of relations. So now we have a chain of if and only ifs showing that C comma A is an element of this set if and only if C comma A is an element of this set. But since C comma A was an arbitrary element of C times A, that means we have proven precisely this statement, which amounts to proving that our two sets are equal. And so this completes the proof. And so yeah, that's pretty much the idea of how you could prove a statement like this. So that's pretty much it for this video.